Welcome to the channel, everyone. The May 2022 papers have been recently released, and to continue my tradition, I will make some videos to provide explanations to the science multiple choice papers in order to help students revise as they prepare for upcoming mocks and, of course, the real exams. The paper that I'm doing in this video is going to be high-level time zone 1 about chemistry. And for copyright reasons, I'm not going to show the actual paper. So I will just take the Richard Thornley approach and paraphrase the questions on a different document and work over there. And I hope this will still provide you with a satisfactory explanation to the questions within the paper. But of course, I hope you guys can get your hands on the actual paper, possibly from your teachers or from online, like Reddit, student room, like IB documents, other legitimate sources. In any event, let's just get started with the first question, which is about some basic stoichiometry. So the question is asking this: 2.67 grams of lead carbonate decomposed, and then they're asking you for the mass of the oxide produced. So this is a fairly basic mole ratio problem. So the equation is actually this: PbCO3 is just given. I'll actually include the state symbol because the question wants you guys to target the solid form by the end. It's actually PbO plus CO2. The mole ratio is just 1 to 1 to 1 throughout. So all you have to do is to figure step one, mass to moles. So 2.67 grams of lead carbonate can be converted into the number of moles of the substance by dividing by its by molar mass, I should say. Sometimes you can say molecular mass. Mathematically, they mean the same thing. But strictly speaking, lead carbonate is not a molecular substance. The numbers are nice enough, and I hope you guys can just recognize that as 0.01. Step 2 is just to use the mole ratios. In this question, the mole ratio is super straightforward. It's just 1 to 1. So the compound of interest, which is lead oxide, should also be the same. Just write 0.01. And then the last step is to convert lead oxide back into the number of grams by multiplying it by its molar mass, which is not directly given in the question, but of course you can always look up the periodic table. The atomic mass of lead is 207. You add the oxygen, 227 plus 16, and that's 223 times 0.01, so 2.23 is the answer. And that will be choice B. Moving on, question 2 is about limiting versus excess. Zinc plus hydrochloric acid, the quantities are given as such, so 0.02 moles of zinc. While for the acid, they give you the volume and concentration. They also give you the balance equation. They're asking for the number of moles of hydrogen produced. I'll just use the Rice approach, which I also showed in the time zone 2 paper. Rice for reaction. Initial. Change. And then end. You have 0.02 moles of the zinc. You have 0.0. But the moles of HCl is 0.01. And to figure that out, what you have to do is to multiply the volume by the concentration. Concentration is instead capital M is what I use. IB uses mmol dm minus 3. Typically, you have to convert the volume into dm cube. Cm cube to dm cube involves division by 1,000. So this should be 10 divided by 1,000, so 0.01. No products as first. And what you have to do is to figure out the limiting reagent. I think it should be quite apparent that HCl is limiting. You have few moles of it at first, but then the reaction requires more moles of HCl, twice as many moles as HCl as you need zinc. So you use up all the HCl. And then you can complete the change row with values that correspond to the mole ratio of 1 to 2 to 1 to 1 in this case. So the final answer is just 0.005, which is choice A but to complete the table, because sometimes they will ask you for the amount of unreacted excess reagent. In this case, for this particular reaction, there should be that many moles of zinc remaining, and then zinc chloride will also be, well, the amount of zinc chloride formed should be this, 0.005. But again, the final answer is A, 0.005 moles of hydrogen. Question 3 is an empirical formula question asking you for the empirical formula of a nitrogen oxide that 8.8 grams of which containing 3.2 grams of oxygen. Fairly straightforward question because NO, so there's 3.2 grams of oxygen. And in this context, the word oxygen refers to oxygen atoms within the formula. I noticed that some students get confused of as in like should they be using the atomic mass or molecular mass? In this context, I'll finish the question first and then I'll discuss the meaning of some of the element names. 5.6, by the way, is 8.8 minus 3.2. And then what you have to do is to convert each mass into the respective number of grams by not times, but rather dividing by the atomic masses. Nitrogen has an atomic mass of 14, 0.4. And then oxygen should be 0.2. So there's clearly a 2-to-1 ratio. Therefore, the formula is just N2O, which is choice B. My earlier discussion about interpreting an element name is quite important in the context of general chemistry. So throughout the chemistry courses, what I believe is that sometimes the element name is used in a way so that the type of particle that is referring to is not like super intuitive. So oxygen itself can refer to a sample of oxygen. And of course, in a sample of oxygen gas under ordinary conditions, we have diatomic molecules. In a mole calculation, in an empirical formula question, where oxygen is part of a compound, whether it is ionic or covalent, we're mostly dealing with single oxygen atoms. So yeah, so make sure that you guys can think your way through and interpret the name of the chemical element in context before you proceed with the calculation. All right, let's get back on track and work on question 4, which is about calculating the relative abundance of 2 gallium isotopes. And by the way, you notice I don't have any choices listed in here. For questions which require you to actually work out the answer and not work backward from the choices, I'm not going to show the choices. I'll just move question 4 to the next page. So given 2 isotopic isotopes and their masses and also the relative atomic mass, you have to use a little bit of algebra. Well, the 4 choices are 40, 50, 60, and 75. So those are not like, it's not like super clear what is the proper abundance of, okay, they asked for gallium 69, by the way. Abundance cannot spell. But we let this be X. You can let it be X percent. I prefer working with X and without the percent, because if you convert the percent, you end up with a fraction denominated 100. And some students actually have troubles like with algebra. But anyways, I'll just write 69 times X, and recognizing that gallium 71, which makes up the remainder of the isotope within the sample, its abundance can be represented by 1 minus X. And there's a times, by the way. And if we expand the left-hand side, just rearrange some of the terms, I think you end up with minus 1.28. So X equals to 0.64. And the closer choice would be, well, it's 64%, and then the closer choice would be 60%. Will they be savage enough to give you a 3 or more component situation? It has shown up in some older papers, but also involves just like setting up an algebraic equation. So I'll give you my iron example here where I'm scrolling towards. Let's make this smaller. Just do this. So when there are 4 isotopes, typically they still have to give you the abundances of 2 of the isotopes, because you have to use one single letter to relate the abundance of the 2 remaining isotopes. So in this iron example, the iron 57 and 58 accounted for 2.4, which means that the other 2 isotopes will account for 97.6. And then you use X and 0.976 minus X, or the percent version. Hopefully you guys, hopefully even that AI student will not be too discouraged in using algebra. It's not that faulty, but I guess it's what it is. There will be times when you can't rely on the calculator. So, well, I mean, in IB multiple choice is definitely a situation where you can't use a calculator. So, of course, you guys will question, like, will you guys have a real life situation where you can't actually use a calculator? Well, no, but there will always be people who can do it faster with a calculator, without a calculator, than you can with a calculator. So, well, the take home message is mental math skills are still important. Moving on, question 5. You're given a successive ionization energy graph with a big jump between the 3rd and 4th ionization. So I'll just replicate the graph inaccurately, but not super accurately. The x-axis scale is pretty tragic, but I think it will still illustrate. And they're asking you which element this atom, or which group this element belongs to. And for this kind of situation, you just be looking for the big jump, because the big jump is occurs when you have take all the outer shell electrons. But this is the first IE, by the way. So the 3rd IE is, the 4th IE is much more difficult to perform than the 3rd IE. And this suggests that the first 3 electrons that were removed, they were in the outermost shell, and then the 4th one, like, has to be in what used to be an inner shell, which means that it was held much, it still held very strongly, and then a lot of energy, significantly more energy is required as the shielding effect decreases significantly. So the answer to this question would be group 13. Had they had group 3, I think this is also a reasonable, group 3 would also be a reasonable answer. In past papers, there have been a question where the choice is, group 16 is the correct choice. But of course, the question does not have, sorry, group 6 is the correct choice, while the question does not have, the choices do not also include group 16. I don't think you can tell from between group 3 versus group 13 in these kind of graphs. In any event, that's the answer to question 5. Question 6 now. So you just need to identify whether nitrogen dioxide, carbon dioxide, and sulfur dioxide are separately acidic, and the answer is yes, all 3 are acidic, and this is some pretty basic, well, acidic knowledge. And the reason that non-metal oxides are acidic is because when they dissolve in water, they will form these oxo acids. And when you have these oxo acid compounds, the hydrogen have some tendency to dissociate as H+. I have never seen them ask for this explanation before, but I think it's still nice to know. Moving on, question 7. Electron configuration of a metallic element, and they have 4 different choices, and this one you definitely need to work with the choices. And these are the valence shell configuration. I hope the answer is quite obvious. Like D3S2 is basically like the 3rd element within the D block, and that's definitely a transition metal. P2 would belong to, well, will be carbon, silicon, and that particular group, so group 14. P4 will be group 16, P5's group 17. So actually, it's not just about the group, they actually give you the full configuration, but in any event, element C is D3S2, and that's vanadium, and that's definitely that's a very typical transition metal, which means that the answer is C. Question 8, why is hydrated copper sulfate blue? It doesn't really matter whether the compound is hydrated or not in general. Well, the anhydrous version is actually white, but I don't think it's generally true that anhydrous compounds are white and or colorless, whilst the hydrated version is colored. But to explain why transition metals are transition metal compound are colored in general, it's all about orbital energy splitting. The mechanism for the generation of color within the transition metal is very often a 3 or 4 marker on the exam. So formation of complex ions causes the energies of the d sublevel orbitals to split into a set of 2 or more different types of energy, and this is followed by an electron transitioning from a lower energy level to a higher energy level by the absorption of visible light. And as a result of the absorption of a certain colored visible light, the observer will observe the complementary color. So the answer to this question is choice D, the statement D saying that light complementary to blue is absorbed when electrons are promoted between d orbitals. So that would be the correct answer. Choice A says that blue light is emitted. Choice C also says blue light is emitted. You get emission when you have previously excited electrons fall back down to lower energy levels. And that happens during atomic emission, like when you look at the hydrogen emission spectrum. So that's a situation where the lamp actually glows in the dark, whereas transition metals cannot be seen if there's no surrounding light. And then choice B says light complementary to the blue is absorbed when electrons return to lower d orbitals, and that's just not how physics works. When electrons go from higher energy level to lower energy level, energy is released, much like when you just drop an object. Gravity causes an object to release gravitational potential energy as the object gains kinetic energy. Moving on, question 9. Formula of the compound between calcium ions and phosphate ions. And this is a fairly basic situation of determining the formula of ionic compounds. And the simple rule is just using crisscross. So my notes has the magnesium phosphate example. And by the way, the name of the compound is calcium phosphate. Choices A and B says calcium phosphorus oxide, and those are just super awkward. And that's not how ionic compounds are named. You name the cation and you name the anion. So PO4 is a proper anion, and phosphorus oxide is definitely not its name. And then using the crisscross rule, which is based on the fact that the electron transaction has to be complete. You can't have excess unaccountable electrons, and you can't have missing electrons. So each calcium ion loses 2 electrons. So bringing in 3 calcium ions can lose a total of 6 electrons, which can be perfectly picked up by 2 PO4 fragments as they gain the 3 electrons to actually become phosphate. So the answer is D. Question 10 now, why ionic compounds in general have high melting points? The question itself asks for the high melting point of sodium chloride, but turns out the answer will apply to pretty much all ionic compounds in general. Choice A says covalent bond between sodium and chlorine atoms is strong, and that's definitely not true because sodium and chlorine atoms, they're actually ions within the substance. The bonding between the 2 types of particles is ionic. That makes B the correct answer because B says electrostatic attraction between sodium and chloride ions is strong, so that is the legit answer. C is about intermolecular forces. There's no intermolecular forces within an ionic compound, ionic lattice. And then finally, D says delocalized electrons cause strong bonding in sodium chloride. That sounds valid for like a metallic substance, like a metallic element or an alloy. Definitely not true for ionic compounds, which don't have delocalized electrons. So again, choice B will be the correct answer for question 10. Now, question 11, for which species can resonance structures be drawn? The 4 choices are drawn out. HCOOH, HCOO minus, which is the correct answer, by the way. The other choices, other organic species. So I would say this, like a list of like molecules or ions that exhibit resonance / delocalization is probably something that you guys should just bear in mind because the list is not really that long. So what are typical species that can do this? Benzene and ozone are some examples of electrically neutral species. But most other electrically neutral species don't do this. Typically, you look at ions, like polyoxyl ions, which like have some singly bonded oxygen atoms and some doubly bonded oxygen atoms within the dot structure. these ions are candidates for undergoing delocalization or exhibiting resonance because they can reposition their lone pairs as well as the second bond of the double bond in quite a few different ways. I'll scroll down a little bit. So for determining resonance structures that can represent a molecule or ion, you typically look for the possibility of bringing in a lone pair. So moving a lone pair from usually a peripheral oxygen, making it becoming a double bond with the central atom. And at the same time, some other double bond will have to, some other double bond pair has to move over to a different peripheral oxygen in becoming a lone pair. So going back to the current question, HCOO minus is the ionic species. It should be the most suspicious one, and turns out it's also the correct one. But if you want to see the full dot structure, so the C-double-O oxygen is electrically neutral, whereas the singly bonded oxygen is negatively charged, and you can consider formal charges. And to obtain the resonance structure, you can just move the electrons around. And what you get is that you get a double bond with the lower oxygen, which also becomes electrically neutral, while the top oxygen takes the -1 formal charge. So this is how you can draw resonance structures. Moving on, question 12. Identify sp3 carbons from a list of simple organic compounds, which include the following. So there's C2H2, C2H2Cl2, and the C2Cl4, and then finally C2Cl6. Well, first of all, sp3 carbons are pretty much always tetrahedral in terms of domain geometry shape. And I hope it's not too difficult to actually draw the displayed formula by recognizing the bonding between the carbon atoms. So the first compound is an alkyne with a triple bond, so those carbons are linear. That's definitely not sp3. In fact, these carbons will be sp. The middle compound is actually like this, I think. The exact positioning of the Cls and versus the hydrogen don't really matter because those are both hydrogen and chlorine form exactly one bond. So you can have the different isomers, but that's not going to affect the total number of bonds and total number of electron domains that the carbons have. So these are sp2 carbons. C2Cl4 should be in the exact same boat as dichloroethene. These are also sp2s. The last compound should be correct. But if you want to see more clearly why, well, you can see that each carbon forming 3 bonds with the chlorine, well, would force each carbon to have 4 electron domains around itself, and that's clearly a tetrahedral carbon and sp3 carbon situation. Moving on, question 13, VSEPR theory applied to xenon tetrafluoride. So what are the electron domain geometries and the molecular geometry of XeF4? So this is a pretty standard, well, higher level, not standard level, but a standard within the higher level syllabus. 6 domain central atom having, and if you draw the dot structure first, how do you draw the dot structure? Well, xenon has 8 valence electrons. If xenon decides to like form bonds, becoming part of a compound. This xenon is otherwise a noble gas, and you can realize that there's a total of 36 bonding electrons. So draw the connectivity. They connect the atoms properly, and then giving each fluorine an octet would allow you to realize that there are 4 electrons that you need to account for. Because right now 8 times 4 is 32. The remaining 4 electrons should be placed on the central atom, making xenon a 6-domain atom. And having 6-domain atom with 2 lone pairs means that the square planar molecular geometry with the lone pairs directly above and below the central atom would allow the electron pairs to space themselves out and experience minimal repulsion, which is what VSEPR is about. So the answer, electron domain geometry is octahedral. 6-domain is always octahedral. And then the 4 to 2 subtype result correspond to square planar molecular geometry. Okay, moving on to question 14, which is the basic calorimetry. supposedly a calculation, but the choices actually provided you guys with the expression instead of the actual value. So energy from burning that many grams of ethanol causes the temperature of 150 cm cube of water to rise by this many degrees. And then the enthalpy change of combustion in kilojoules per mole is asked for. For this question, all you have to do is to apply the standard formulas involving, well, two formulas. So Q equals to MC delta T. And then you put delta H equals to negative Q over N. And none of the choices actually had a negative sign, but I insist that the negative sign should be here because for an exothermic reaction, like energy conservation, like if the system, if the surrounding water gains thermal energy, that means that the system lost chemical energy. But the sign is not what this question is about. So M would be the mass of the water, not the mass of the ethanol, by the way, that you're transferring the chemical energy. Well, the heat energy, which is what the chemical energy has become, is going to be transferred to a body of water, and then Q equals to MC delta T deals with heating. 4.1 is the C value, which is quite standard. Temperature change is 10.5, and there's no need to convert the 10.5 into Kelvins because we are calculating a difference in temperature rather than the actual absolute temperature. So all this needs to be divided by the number of moles of ethanol. I'll just need the negative in front, just to be more formally correct. And then you can divide by the number of moles of ethanol, which is mass divided by molar mass. 0.25 divided by molar mass, which is 46.08. However, this expression so far would have given you the energy change in joules per mole. And then to convert joules into kilojoules, you simply need to divide by 1,000. So choice A will be a trap answer without the kilo. Choice B is correct, while choices C and D both had the 273 plus the temperature change. I don't remember seeing many students making the 273 mistake for this kind of calculation, but IB typically loves to have those at their trap answer, but this is a very easily avoidable trap. Moving on, question 15, which is about calculate the enthalpy change of a reaction. I did not write the reaction here, so let me just write the equation here, which is CH2CH2CH3 plus HBr becoming product, which is, I just write C4H9Br. And then the delta HFs, which are given. The alkene is 0.1, HBr is negative 36.3, and then the product is negative 156.0. There's a general formula that if you guys can remember is this. So the energy change of a reaction is, people just keep saying that energy change equals the product minus reactant, and that's I mean, it works on the exam, but it's a very poor way of explaining how things work. Well, how things work, well, you typically begin with the reactants. And this is an energy level diagram, and let me make more space. The products usually, I'm guessing this is exothermic, but it's not too important. So the thought process, the hypothetical reactions involves, well, the formation of, well, first of all, you're going to form the elements from the reactants. And when I say element, I mean elemental substance and not just a simple atoms. You're making carbon, hydrogen gas, and bromine molecules. And then according to the definition of delta HF, the 0.1 kilojoules per mole and the negative 36.3 kilojoules per mole are the energy changes when you convert carbon and hydrogen and bromine into the reactant molecules, respectively. So for our current process, let's get rid of those. We have to do plus well, negative 0.1 plus the negative of negative 36.3. So negative 0.1 double minus so that's the energy change for converting the reactants into elemental substances, which do not actually occur when you perform the reaction. However, Hess's law problems do not involve real process. Like Hess cycle, like the component reaction within Hess cycle are rarely going to be reactions that actually occur. And back to the current question. So what we have to do is to finish off the Hess cycle by converting the elemental substances into the actual final product, which involves a release of 156 joules or kilojoules of energy. And for this question, you actually need to crunch the numbers. So if we do, well, I'll just combine the negatives together. So 36.3 minus 156.1, and that would equal to negative 119.8. And that makes choice C the correct answer. Question 16 now, identify a compound with the highest lattice enthalpy. The four choices are as follows. Sodium oxide, which is the correct answer, by the way. Potassium oxide, sodium sulfide, and potassium sulfide. So here you have to choose between the cation, or the sodium versus potassium, and then the negative ion, oxide versus sulfide. It should be super straightforward. The method for determining the correct ionic compound that has a stronger lattice enthalpy would be simply size and charge. Hang on, I went too far. So in general, ions with higher charge density, so higher charge and or smaller radius, which form stronger ionic bonding because of physics. And the physics behind ionic bonding is just the force, attractive force. You can formulate your argument in terms of energy as well, but I think force is more straightforward. K Q1 Q2 over R squared. So physics student will definitely recognize this. Chem student need to use this qualitatively, I guess. So the higher the charge, the stronger the force, whether attractive or repulsive. Meanwhile, the smaller the separation between the charged particles, the stronger the force as well. And then, so here for this question, you're comparing sodium versus potassium. Well, sodium is clearly smaller than potassium because elements down the periodic table typically have higher atomic and also ionic radii. And same thing goes for oxide versus sulfide. Oxygen is above sulfur. Oxygen or oxide ions are smaller than sulfide ions. Therefore, the clear-cut answer is sodium oxide. So choice A happens to be. Okay, moving on to question 17. In which reaction does entropy decrease? It's super straightforward because all you need to do is to notice the change in phase of the reactants versus products. The four choices involve number one, sodium chloride dissolving. Solid particles are much more ordered than aqueous particles. So the entropy definitely has increased because there's much more disorder in the products compared to the reactants. So that's wrong. Choice B is a reaction between metal zinc plus sulfuric acid, which is an aqueous substance. You end up making zinc sulfate, which is soluble, so it stays aqueous. You also end up making hydrogen gas, and gas particles have very high entropies because gas molecules can fly around within the space. So definitely not B. Choice C is the correct answer because you end up with two gases reacting with each other to become a solid. I want to say an ionic solid. It doesn't really matter whether the solid is ionic or not. A solid definitely has higher orderness and lower entropy than the starting gases. The last choice is the decomposition reaction. It's copper carbonate solid becoming copper oxide, which is also solid, plus CO2, which is the gas which correspond to the system having much higher entropy than before. Moving on, question 18 is about interpreting a monitoring graph. So a monitoring graph during rate of reaction is one that shows how an amount changes over time. And here the question describes, so what happens when we have, okay, the setup, I did not write out the setup. So here is a setup. So we have a limestone plus HCl reaction. BaCO3 plus HCl. 2 is not too important for this question. And then you make calcium chloride plus water plus carbon dioxide. And the graph shows how masses decrease. And the mass decreases because carbon dioxide is a gas. And when you produce a gas from a solution, and I'm guessing they would be performing the reaction on a balance, on a beaker on a balance, so the carbon dioxide gas just flies away. It's super important to know that the HCl was in excess, so they tell you that this is an excess. And they're asking you for what the new graph is going to be like if the experiment is repeated with acid that is twice as concentrated. So two things to consider, as you can see. You have to consider how the initial rate changes, and you also need to consider how the final amount changes. In fact, those are so the 4 choices given within the question. The initial rate depends on collision theory factors. So increasing the concentration of HCl, the initial rate definitely increases. So you have a steeper graph at first. So it can be like this. It's also possible that you end up losing more mass. And that is when you have to consider stoichiometry, mole ratios. The HCl was in excess at first. So doubling the concentration of the acid will also correspond to more moles of acid present, simply because moles equal to conc times volume. Having more moles of acid here will not cause more mass to be lost, simply because the acid was already in excess. Like had calcium carbonate been in excess and then you use more concentrated HCl, then the rate is faster, and you should also end up losing more mass because you will be forming more CO2 due to moles. So higher rates, but the graph levels off at the same final mass, which makes choice B the correct answer. Clear screen. So question 19 now. They give you 4 reactions and they ask you which reaction is best monitored using the colorimeter, which measures the color intensity at a specific wavelength. So the 4 choices will be number 1, Ki plus CO2, KBr plus CO2 like that. B is about copper plus sodium sulfate. C, NaOH plus HCl. The last one is some organic reaction. And what this question actually tests you is not really about the rate of reaction, but rather whether you actually have a legit reaction between, like for each choice, does the mixing of the 2 chemicals actually produce a reaction? Because turns out choice B and D are both non-reactions. So will the metal undergo displacement to become copper sulfate, which is colored, plus metallic sodium? Well, it works on paper. It's not going to happen in reality. And the reason is actually for redox, like reactivity series. Copper is way below sodium within the reactivity series. So you have to use your redox knowledge to recognize that this is a non-reaction. You can write what seems to be a sensible reaction on paper. In real life, it won't happen. So even though copper sulfate is blue, and then sodium sulfate has no color, the reaction won't actually happen. Choice D is the other non-reaction because you have an alcohol added to potassium dichromate. This is the tertiary alcohol, and if you remember your organics, tertiary alcohols don't get oxidized by these like dichromate or like permanganate oxidizing agent easily. So there's also a big answer So even though if the dichromic actually reacts, typically you need to use an acid as well. But here, the alcohol itself, well, is incapable of being oxidized under ordinary conditions. Had there been a reaction, then you'll see the famous color change of orange becoming green due to the formation of this chromium 3+. But dichromic is not going to react with a tertiary alcohol. So A is the correct answer because C is a real reaction. However, all the reagents like the base and the acid, as well as the resulting salt, they are all colorless. So there's no detectable color change during the reaction. And A will be the correct answer because when you react KBr with chlorine, you get the displacement reaction. You get bromine, which is brown, whereas Cl2, chlorine water or chlorine gas, both are very palely colored substances. So choice A is the correct choice. Okay, moving on, question 20, which is about analyzing the order of an SN reaction. Well, the question says, shows you a table for the hydrolysis of a halogen alkane. So hydrolysis of halogen alkane is just a nucleophilic reaction. So the table is like this: 0.1, 0.2, 0.2, 0.01, 0.01, 0.02. And the rate is like 5, 10, and I'll just change up. I'll just re-represent the numbers like this. And the question asks, well, which of the following statements are correct? So is a reaction first ordered with respect to RCl? And you can see that by doubling the RCl concentration while holding the hydroxide ion concentration constant results in the rate that is, it's not quite doubling, but it's close enough. So doubling RCl concentration causing the rate to double is indicative of RCl, indeed a first order reaction by definition. So the first statement is correct. The second question asks for whether the reaction is second order overall. For this, you also need to look at the rates of the order with respect to the OH minus. In terms of we are in the same boat because doubling the hydroxide concentration also causes the rate to double. So therefore, the answer is, therefore, the second statement should be correct because 1 + 1 is 2. And then the last statement, the reaction proceeds by an SN2 mechanism. And the 2 within S2 refers to the fact that the reaction is second order overall, which is definitely the case here. Wait, hang on, I need to check the answer. Well, how come this is? Actually, no. I look at the one question. I was looking at question 21A. Why is the answer A, but turns out it's D? All 3 is correct. Never mind, excuse me. Now, question 21, Arrhenius equation. They give you the Arrhenius plot. They give you a ln T versus K plot, and they give you the grades, a little bit graphical details. So they say this is -2 and this is 0.06. The thing about the Arrhenius equation is that it's not given in the formula book, but they actually it's given in the formula book, but you won't have the formula book for paper 1. They presented you with the no log, like the exponent version of the Arrhenius equation within the equation. So hopefully you don't do math AI because I'm not sure whether you guys will be able to rearrange. I think AI needs to learn log, so I think you guys should still be able to log the equation as needed. But hopefully you guys just remember that in order to calculate the activation energy of like a reaction when you construct the Arrhenius plot. The approach is to just note the gradient of this Arrhenius plot and then take the negative of it and then multiply by R. And the derivation, I mean, you can work it out during the exam by taking logs and then comparing the equation with y equals mA plus c. With natural log of an exponential term, or natural log and e undo each other. you'll have negative EA over R, and I write the equation like this, and then you can recognize that 1 over T is the x-axis quantity, ln K is the y-axis quantity, so the ln A will serve as the y-intercept, whereas the gradient of your Arrhenius plot is negative EA over R. Therefore, the activation energy equal to the gradient times R. And for this particular question, the choice A is the correct answer because the gradient is 2 over 0.06. Where is it A? They say negative. Well, I guess yeah, the activation energy is the negative of the gradient because the Arrhenius plot gradient is always negative. So choice A, which has no negative overall, is the correct answer. Okay, moving on, question 22. It's bigger. So they give you the equation, they give you the Kc value, and they are asking you what happens to the Kc value if you redefine the reaction. So the redefined reaction is this 2ICl becoming Cl2 plus I2. So the redefining the reaction by number one, flipping it, and number two, multiplying all the coefficients by 2. So if we double the coefficients, what you have to do is to square the OKC value. And they're not actually asking to square the 454, thankfully. They're also asking, but you have to address the flipping of the equation. Flipping an equation, well, you have to take reciprocal. And these are all mathematically provable, as you can see. So 1 over 454 squared is the correct answer, and that's choice D. And then question 23, which is based on the same equation, and they want you to find you're using the same Kc value, and then you have to use the Kc expression, I guess. So, and you're using the old definition. So ICl, my bad, not HCl, over Cl2 to the power half. It looks weird, but then it is what it is. When the equation has fraction coefficient, you do need to use fraction powers within the Kc expression. And they're asking for the equilibrium ICl concentrations. So if you just rearrange this, the 454 times, well, power half is the same as the square root. So root something times root something is just the number is inside the root itself. So choice B is the correct answer. Okay, moving on, question 24. And identifying Bronsted-Lowry acids of a given equation should be super straightforward as long as you remember what is a Bronsted-Lowry acid. So a Bronsted-Lowry acid is a proton donor. So you compare a species before and after a chemical reaction, and you can see that CH3NH2 versus CH3NH3 plus. So this guy clearly has an extra H plus. So this guy could have been the proton donor for the reverse reaction. And then for the other conjugate pair, water versus hydroxide. So water definitely has 1 more H plus relative to hydroxide. So this is, for this pair, water will be the acidic species. So the answer will be H2O and CH3NH3 plus. So choice B. Question 25 now, which 0.01 mole per dm cube aqueous solution has the higher pH? So they give you 2 acidic species and 2 basic species. It's also it's really, again, basic knowledge that sodium hydroxide is a much stronger base than ammonia. So you can definitely, and also high pH corresponds to basic or alkaline. So you can definitely rule out the acids. And then sodium hydroxide, being the stronger base, generates more hydroxide upon dissolving in water. Therefore, it should produce a solution with the highest pH. Question 26 now, describing the role of the chloride ion within an organic reaction in terms of Lewis theory. So under the Lewis theory, a Lewis base is an electron pair donor, while the Lewis acid is the electron pair acceptor, as the Lewis base and acid form some kind of data covalent bond. So here chloride definitely has a lone pair. In fact, it's got 4 lone pairs. While the C2H5 plus is a carbocationic species with a carbon that is only got 6 electrons, so it's got an incomplete octet. It's definitely reactive in the sense that it will want to gain 2 more electrons. So the carbon species, the carbocation is definitely your Lewis acidic. So the chloride is a Lewis base because it donates a pair of electrons. So choice A will be the correct answer. Question 27, ranking the pH of 4 different salts. Salts can be perfectly neutral, it can be slightly acidic, and can be slightly alkaline. So the perfectly neutral salt will be KBr. The KBr is perfectly neutral because KOH and HBl are both strong acids. So that means that you guys need to know that HBr is a strong acid. The other choices, HCO NH4 is a weak salt. Weak salt, there are special treatments. You can expect to have a pH close to 7, but it's not going to be exactly 7. It has shown up in one rather old paper, like 2013 somewhere. A weak salt, and you have to consult the relative strength of the acid, the weak acid and the weak base doing their own thing. So if the strength of the weak acid corresponds to a higher K, then if the weak acid has a high K, then the weak base has Kb, then it will be overall acidic. And I think in this case, it's actually it's indeed the case. NH4 plus, if you look up the data book, then NH4 plus has a slightly, actually you had to calculate it because the formula book has NH3 and the HCOOH, from which you can work out the Ka and Kb values of NH4 plus and HCO minus respectively. But for this question, it's not important. Because NH4Br is a famous acidic salt. So NH4 plus undergoes salt hydrolysis. Well, how do you know that NH4 plus undergoes salt hydrolysis? Well, it turns out you just need to know it. I'll show you my notes afterwards. But definitely not NH3 plus. Br minus is the conjugate base of a strong acid, so it won't do anything in aqueous medium. The last one is a basic salt because HCOO minus is a conjugate base of a typical weak acid, which means that it will undergo salt hydrolysis. Whereas K plus will not do anything in solution in contributing H plus. So NH4Br should be the most acidic salt, and HCOOK is the most alkaline salt. The only choice, like among the 4 that has NH4Br at the bottom of the list and HCOOK at the top, is choice C. Just quickly go through my pH analysis note section. So a strong salt has a pH of 7 because none of the hexaaqual ion, cation, and also the halide, the conjugate base of the acid, they are both too weak to produce any significant amount of H plus or OH minus to cause the solution's pH to deviate from 7. So these explanations are needed for paper 2. Paper 1, you can just use something more shallow. It's much faster. So this is what everyone knows, I trust. But then for paper 2, you may need to write an equation to justify and not just say strong means pH 7. We can just move on to question 28, I guess. It's a redox question now. So reduction of a sulfur-containing species to produce SCl2. The 4 choices are as such. So to figure out the correct species, well, you have to recognize that the species need to undergo reduction, which involves a decrease in oxidation number. You can use the oxygen definition, you can use the electron definition some other times, but I think the oxidation number treatment is the most reliable. Because SCl2 has an oxidation number of +2. On the left-hand side, you've got some ionic species, some electrically neutral species. Not everything has O, not everything has H. So if you just crunch the oxidation number, you'll see SO4 has an oxidation number, a sulfur within SO2 has an oxidation number of +4. So that's why it's the correct choice. If you work out the oxidation number of sulfur is 0. H2S is -2 because hydrogen is definitely the positive atom within H2S. S2O3 minus, you probably need to use a little bit of algebra. So you can write 2x, where x is the oxidation number of sulfur, plus 3 times -2 because oxygen's favorite oxidation number is -2, equals to the ionic charge, which is -2. And I think if you finish off the calculation, you end up with the conclusion that sulfur began to be +2. So S2032 minus becoming SCl2 is not the redox reaction. Now, question 29, how many electrons are needed to balance the half equation involving NO3 and NO as the starting and final form of nitrogen? They do give you the equation with H plus and E minus shown. So a super fast approach is just to work out the oxidation number. So the nitrogen here is +5. Because you have what, X plus 3 times -2 equals to -1. X equals to 5. And then NO, oxygen is -2, famously, so nitrogen is 2. And then +5 becoming +2 is a 3 electron reduction. And that's what the question is going after. If you don't want to take the oxidation number approach, then you can just balance everything else, just balance all the atoms and all the particles one at a time. And you can begin by balancing oxygen first by dealing with the water. You can't really change these two because these two need to be have the same coefficient in order to maintain nitrogen balance. So the only way to fix the oxygen balance is to alter the water coefficient. So you have 2 waters, which provides 4 hydrogen atoms. So you can introduce 4 H pluses on the left-hand side. And then to balance the electrons, the right-hand side is electrically neutral, while the left-hand side is 3 plus before you worry about the electron. Accordingly, you need to introduce a 3 in front of the electron. Either way, the answer is C. Question 30 now, what are the products when dilute aqueous carbon nitrate is electrolyzed? They provided you with the reduction potential of, actually they give you the oxidation potential of copper to becoming copper 2 plus of -0.34. I don't think you need, I think you probably should memorize that copper is more difficult to reduce than H plus, because H plus to H2 reduction has a reduction potential of 0 by default. For this, I'll just show you what I believe is the best approach. To figure out the correct species that you form at the cathode, which is in general easier decision than the anode process. At the cathode, if the metal has low reactivity, lower than hydrogen, copper is definitely less reactive than hydrogen, then it will be easier for the copper ion to go back to become metallic through reduction. In this case, copper is indeed, like I said, copper is less reactive than hydrogen. Therefore, formation of metallic copper will occur preferentially over the formation of hydrogen gas. So the cathode process, you make copper metal. Meanwhile, at the anode, the identity of the negative ion would determine what gas you form at the anode. So oxidation of nitrate is unheard of under ordinary conditions. Therefore, by default, it's going to be some particle of water. So you can either involve water itself, or you can involve the hydroxide, which can be formed as water undergoes dissociation. But either way, you're going to form oxygen as the anode oxidation product. So the answer for this question is A. Now, question 31. Cells in series, so silver nitrate, not sodium, silver nitrate and nickel sulfate connected in series. And when you have cells connected in series, you have to recognize that the number of electrons involved at each electrode surface will be the same. So silver is a 1 plus ion, getting reduced to become silver metal. Nickel is well, clearly 2 plus, also becoming the electrically neutral metal. So 0.959 gram this happens to correspond to 0.01 mole because nickel has an atomic mass of 59. And the electrons should be treated as like a reactant quantity in electrolysis. So to form 0.01 mole of nickel, you need to bring 0.02 moles of the electron. And because of cells in series, the electrons involved in the silver reduction is also 0.02 mole. And because silver reduction is a one electron process, you should also end up with 0.02. I keep writing wrong. 0.02 mole of silver metal. And then to figure out the number of grams, you multiply by the atomic mass, which is 108. So 2.16. Moving on, question 32. Now we are into organics. So serine is an amino acid, and yeah, the question actually provided you with the structure, so no worries there. The question did not say that it's an amino acid, but again, because the structure is provided, even the name serine itself is not too important. So the functional groups in this molecule, well, NH2 is amino, and you have to distinguish between amino versus nitro, which are also present in two of the choices. So nitro is NO2. But you also need to recognize the other functional groups. So they have carboxyl, carbonyl, and hydroxyl. So this is definitely hydroxyl. Is this also hydroxyl? It's not wrong, but in the presence of the C-double-O, much of the C-double-O itself can be regarded as a carbonyl. But because C-double and O single H are bonded together, this entire group is called the carboxyl, which is the better answer. So it's got the carboxyl and then it's separately got the hydroxyl. So I don't think this is like one of the best questions because like carboxyl compounds belong to a subclass of carbonyl compounds. And that's what I believe to be true according to some like the Oxford study guide. Yeah, so carboxyl is encompassed under carbonyl, whereas there's some other functional groups which still retain, which can still be classified as strictly a carbonyl compound. But for this particular question, the answer should be amino, carboxyl, and hydroxyl. Well, I guess choice B has hydroxyl and carbonyl, and I guess we're calling the COOH as a carbonyl compound. It's not wrong, but the carboxyl is more descriptive. Let's move on. Question 33, which asks for compounds that belong to the same homologous series. Well, the definition of a homologous series is the compounds within a homologous series. Wait, where's my homologous series definition? There you go. The most important one in terms of recognizing a homologous series by referring to a structural formula or names is that they have the same functional groups, and then like members within the series have they differ by exactly one CH2 unit. The choices, well, first choice propanol, propanol, and propanol acid, they are all three carbon compounds, but they all have different functional groups, so definitely not true. B suffers from the same drawback, so propane, propene, and propyne, they have the same number of carbons, but definitely not different numbers of CH2s, and they also have different functional groups. C, hexane 1O, hexane 2O, and hexane 3O, they all have the same functional group, but they all have 6 carbons. So those are isomers of each other. Last choice, ethanol, propan 1O, and butan 1O would be the correct choice. Moving on, question 34, which reagents and conditions are best for converting propan 1O into propanoic acid? So a primary alcohol becoming a carboxylic acid is best achieved by using a distillation apparatus, by using, no, I take it back, definitely not distillation. Distillation is for making the aldehyde. Okay, this. Distillation allows you to isolate the aldehyde, which typically has much lower binding points than both the alcohol and the carboxylic acid. And this in turn has to do with intermolecular forces. So to produce a good yield of the carboxylic acid, you need to use the so-called reflux apparatus, or an upward condenser, which allows any organic vapor that's trying to escape the system. You force the vapor to come into contact with a cold surface in contact with cooling water, so that the vapor goes back down, stays in contact with the oxidizing agent. So you have to use reflux with the correct oxidizing agent. And the two agents that you have to choose from would be potassium dichromate, which is the correct choice, and AlH4, which does the opposite, is the reducing agent. So the answer therefore is A. Moving on, question 35, role of NO2 plus during a benzene nitration reaction. And they did give you the reaction, but hopefully they don't even need to give you the reaction. Benzene nitration only occurs through a unique mechanism as such. So NO2 plus is a species that the nitrogen definitely does not have a lone pair, and the mechanism just involves. If you have to, I don't think you'll ever need to draw out the structural formula for the NO2, the nitronium ion, but the mechanism involves some rearrangement. So the benzene electron is attracted towards the nitrogen atom, which has I think it has the positive formal charge as well. So the NO2 definitely it's electron deficient, so it's definitely an electrophile. Meanwhile, this reaction is definitely a substitution reaction, because you incorporate the NO2, but then you have to kick a hydrogen atom. So overall should be choice A. Question 36, which is molecule Z that's formed in step 1 of a synthetic group, and the synthetic group just involves the formation of aminobenzene from nitrobenzene. So nitrobenzene becoming aminobenzene is an overall reduction reaction. And so you make a phenylammonium species, and that's the correct answer, choice B. The phenylammonium species can then undergo an acid-base reaction. It can be deprotonated by the base NaOH to become the electrically neutral amine. Moving on, question 37. So they give you two alkenes and then ask you for the EZ designation. So the alkenes are as such orthogonal. The second alkene is just, I think it's just butyene. Yep, indeed. But the butyene is drawn like this. The rule for designating E versus Z isomer is if the high priority functional groups are across each other from the double bond, is a Z isomer. So how do you determine priority, you guys wonder in general? So for each carbon, you look at the two groups attached. And you look at the atomic number of the first atom that's bonded to the carbon. Carbon is definitely higher priority than hydrogen. So the priority is for the first carbon is on near the bottom, whereas the high priority on the second carbon, so the C2H5 is a high priority group. Well, the atom that's immediately bonded to the carbon, well, they're both carbon themselves. So you have to look further downstream. So I'll just draw the C2H5 structure, which is like this. So the first atom does not settle any difference, but clearly the second atoms will, because for the C2H5 group, the first carbon is bonded to CHH, whereas for the CH3 group, the carbon is bonded to HHH. So the top definitely has a higher priority. And when the priority groups are across like this, so this will be a trans isomer, or I guess you should say E isomer, E for opposite in German, I think. This other compound is clearly an E isomer as well. So that's E butyene. On the left hand side, you have got E 3-methyl pentene. Either way, choice A is the correct answer. Question 38, you are presented with an NMR spectrum with 3 peaks. So that the number of peaks should be the first thing that you look at. So 3 peaks means that there are 3 types of proton environment. Does propanol have 3 environments? The answer is yes. So in terms of propanol, choice A is the correct answer already. 1 type, 2 type, 3 types. The other choice of propanol is perfectly symmetrical. Choice B is propanol, but propanol has 6 hydrogens and they are all equivalent. Propane is like this. So also there's some symmetry making the first carbon and third carbons equivalent. So propane should only have 2 peaks. This is 1 type. This is the other type. The last one is methylpropane. Methylpropane also has 2 types. So the CH3s are actually all equivalent. So some students may get confused between they recognize the symmetry, but then they don't recognize that the CH3 is also classified the same. So propanol should be the correct answer. Question 39, what is the index of hydrogen deficiency of a molecule whose structural formula is given? So this is Panadol, painkiller, and this is the structural formula presented in the paper. I've seen students actually who tries to come up with the structural formula by counting the carbons and counting the hydrogens, and then use the IHE formula. That's not how it's supposed to be done. When you're presented with the structural formula, all you're supposed to do is to count the features. So benzene ring, you definitely want to relocalize the double bond for this exercise. You have 3 unsaturations within the benzene ring due to the double bonds. The ring itself is 4th saturation, and then you've got a C. So you've got a C double elsewhere within the molecule. So there are 5 features that correspond to 5 unsaturations. Yeah, the IHG formula is number 1 not given, and number 2 is difficult to remember because it's very difficult to memorize the derivation for it. Yeah. So for molecule structural formula is known. So you're not supposed to use the formula. You're supposed to just count it. And yes, I've seen students who just try to come with the formula, and that's just a waste of time and effort, and it's also a mistake-prone process as well, because it's like even the pros can actually miss out on some of the hydrogens. Okay, last question, which is about analyzing a mass spectrum. So the mass spectrum has peaks at 60, 45, and 43, and there's some other minor peaks due to isotopomers, but I don't think those are important for IB purpose. Like you have to know the halogen isotopomers, but carbon and oxygen isotopomers I don't, or like hydrogen isotopomers I don't think they have ever shown up before. So choice A is like this. The molecular mass is not even 60, because 60 is like the molecular ion peak. So the M plus is not even 60, so not correct. B is CH3OCH2CH3. The molecular mass is actually 60, but this is actually wrong. It's wrong because you can't really account for the peak of 43. So to get 43 from 60, you have to subtract 17. There's no way that I can cleanly cut off a fragment whose mass is 17 from the structural formula. So you may not want to immediately rule it out, but you should definitely feel suspicious about B being the correct answer. And C, carboxylic acid, is actually the correct answer. Ethanoic acid, number 1, it has a mass of 60. Secondly, you can break off the CH3. That's 15. 60 minus 15 is 45. That's the mass of the COH. It's also possible that you break off the OH, the hydroxyl inside, and then the remaining fragment, because OH is the fragment who has a mass of 17. Therefore, choice C is the correct answer. And then choice D is halogen alkane. I don't think that has. You definitely cannot break off a 17. I think chlorine has an atomic mass of atomic number of 17, and maybe that's what I'd be trying to confuse students with. But in any event, I think this is a longer than usual video, so I'll try to add timelines to the video so that you guys don't have to spend too much time watching the entire thing. But of course, if you guys want to watch the entire thing, I'll be happy about that as well. So hopefully you guys find the explanation useful, and you can watch my Time Zone 2 video, which I have previously done already. And I'll also try to do some physics and biology before the November exams. All right, thank you for watching. See you guys next time.